All right, let's get right into it. For a whole lot of engineers, the phase diagram is one of those things you see in a textbook, maybe it's hanging on a lab wall, and then you kind of try to forget about it. But what if I told you it's one of the most powerful working tools you could have? Today, we're going to take it off that wall and actually put it to work.
I mean, seriously, if you've ever stared at a chart like this and just felt a wave of confusion wash over you, you are so not alone. It's a really common experience for these to look more like abstract art than some kind of practical guide.
And there's a reason for that. It's this well-known thing called the theory to application gap. So many of us learn the definition, right? But then when it's time to actually use it, to make a real engineering decision, things get a little fuzzy. So let's clear all that up right now.
To do that, let's forget about complicated metals for just a second and think about a cup of tea. You know how you can dissolve a ton of sugar in hot tea, but as it cools down, some of that sugar starts to crystallize out. Well, this chart here, it's just a phase diagram for sugar and tea. It's a map that shows you the exact boundary between all dissolved and oops, sugar's crashing out. And that, at its heart, is all a phase diagram is, a map of a material's behavior.
So yeah, the formal definition is exactly that. It's a map. But instead of showing you roads and cities, it shows you the stable states, or phases of a material under different conditions. It tells you, hey, at this temperature and this composition, your material is going to be a liquid, or a solid, or a very specific mix of different solid structures. It's your GPS for materials.
So why do we care so much about these maps? Well, because they are incredibly practical tools for making decisions. They let us cook up brand new alloys for very specific jobs. They let us design super precise heat treatments to get the exact properties we're after, and they help us figure out how to shape a part without it cracking. They even help us troubleshoot why a component might have failed out in the real world.
Okay, so with that foundation, we're going to zoom in and focus on what is arguably the single most important map for the materials that build our modern world. I'm talking about the iron-carbon phase diagram.
And here it is, the big one. Yeah, it might look a little intimidating, but just remember the analogy. This is just a map. It's the essential blueprint that tells engineers how to navigate the world of iron and carbon to create basically everything from skyscraper beams to the engine block in your car.
Now, to read any map, you've got to know the key landmarks, right? For us, that means knowing the key phases. There are really just three you need to know to get started. First, you've got austenite, which only exists when things are really hot. Think of it as the hot, uniform starting point for any heat treatment. Then, at lower temperatures, you have ferrite, which is basically soft, bendy iron. And finally, there's cementite, which is this super hard, super brittle compound of iron and carbon. Those are our basic building blocks.
And here's the absolute key. Steel isn't just one thing, it's a mixture of these different phases. By controlling the exact recipe, the amount, the size, and the arrangement of that soft ferrite and that hard cementite, you can totally customize the steel's properties. You can make it tough, you can make it hard, you can make it easy to machine. The phase diagram is your guide to creating that perfect mix.
Okay, theory's great, but let's actually put this map to use. We're going to walk through a really practical scenario. How an engineer can take a regular piece of steel and, just by following this map, completely change its properties using a simple heat treatment.
The process is actually pretty straightforward. It's really just two steps. First, we heat the steel up to a very specific temperature to basically hit the reset button on its internal structure, turning it all into pure austenite. Then second, we cool it back down in a very controlled way to transform that austenite into the final structure that we actually want.
All right, let's start our journey on the map. We're going to take a super common steel that has about 0.4% carbon. So that's our position on the horizontal axis. Now, we're going to heat it up to about 850 degrees Celsius, which moves us straight up the vertical axis. And you can see that path takes us right into the middle of that big region labeled with a gamma. That's our austenite phase.
So what happens when we get there? Well, at 850 degrees, any of the old structure, the ferrite, the cementite, it all just dissolves. Everything transforms into this beautiful, uniform, consistent structure of pure austenite grains. We've basically created a blank canvas. It's the perfect, predictable starting point for whatever we want to do next.
So we've got our perfect, uniform austenite. The million-dollar question now is, what does our map predict is going to happen as we start to cool it back down to room temperature really, really slowly?
This right here is where the magic happens. This is where the map becomes our crystal ball. As we trace our journey straight down from the austenite region, the very first boundary line we cross is called the A3 line.
And the map tells us that the second we drop below this temperature, a brand new phase, that soft ferrite, is going to start to form, popping up right at the boundaries between our austenite grains.
Okay, so we keep cooling down slowly, and we hit the next major boundary, the A1 line. You can think of this as a huge climate shift on our map. When we cross this line, all of the austenite that's left transforms all at once. But it doesn't just become one thing. It becomes a finely layered mixture of both ferrite and cementite, a structure called pearlite. So by the time we get to room temperature, our final structure is a composite. We've got those first ferrite grains, plus this new pearlite mixture.
So, we followed the map, we predicted a final structure, but who cares? So what? Let's talk about the payoff and why on earth an engineer would go through all this trouble.
This is where it all comes together. That cooling journey we just took, the speed of that journey completely changes the final product. If we had cooled down much faster, we'd get fine pearlite, really thin layers that make the steel strong and hard, perfect for a cutting tool. But because we cooled it slowly, we get coarse pearlite, thicker layers that make the steel softer and more ductile, something you could easily bend. By controlling the path on the map, we control the outcome.
And get this, it's not just what phases are there, but their shape. On the left, that's gray iron. The carbon forms these sharp flakes, which makes the iron brittle. It's great for an engine block that needs to be rigid, but it would shatter if you hit it. On the right, just by changing the process, a different route on the map, the carbon forms little round balls. That's ductile iron, and it's incredibly tough. It's perfect for a suspension part that needs to take a hit. Same ingredients, different map coordinates, totally different performance.
And that brings us right back to the main point. The phase diagram is not some passive wall poster. It is an active, predictive tool. It lets an engineer look at a property they need, say high strength, and then work backwards to design a specific process, a specific path on the map that will reliably create the exact internal structure to deliver that property.
This idea of using maps to predict outcomes is just fundamental. And you know what? It's only getting more powerful. Researchers are now looking at AI as a sort of co-pilot, something that can help engineers navigate these incredibly complex material landscapes with even more speed and precision than ever before.
Which kind of leaves us with one final big thought. The iron-carbon diagram we've been looking at, it's over 100 years old. If engineers have managed to do all of this with just this one map, what on earth becomes possible when AI starts to discover and draw entirely new, more complex maps for materials that we haven't even dreamed of yet?